name is Engineer, and um, I would just love to continue from where we stopped in our previous class. Okay. Quickly, without wasting much time, I hope you can see my screen and you can also hear me clearly. Alright, that is so. I'll shift immediately. Okay. In our previous class, we started talking about practice, process simulation, and we explained that if the simulation for all forms of chemical processes, especially with respect to the oil and gas um, industry. All right, and from there we went on to talk about its uniqueness and some other features. So today we'll continue with that and quickly see how we can go into um, fluid characterizations and basic equipment. That will be a very good landing for every one of us. All right. So okay. So we'll continue from this area of degree of freedom that we're talking about in the previous class. We explained this uh, process of degree of freedom, saying that it's like in this equation where the degree of freedom in process balance is equal to the number of unknown variables plus the number of reactions minus the number of independent material balances and number of relations. Then we use this diagram to explain it. But if you remember very well, we had previously used this to explain the degree of freedom in basic here, where you have some number of variables and equations. Okay? So that explains our degree of freedom um, in our simulation. We usually have feeds that come in, and those feeds we could have some families, that's like top collections and bottom collections. Okay? Top and bottom, that's the ones that we take out the continuing process, then the ones that are rejected, those ones can also be processed into another area. That's what this diagram here is representing. Okay. Without much waste of time, I would just want to explain these variables that I was talking about. Now, under degree of freedom today, I have what called the independent variables. And under the independent variables, we have two types, two classes of independent variables. Please take note of everything I've seen. Alright, and also do some studies too on the end. Alright, two classes of independent variables. We have the intensive variables and then we have the extensive variables. Alright, intensive variables and the extensive variables. The intensive variables comes from the x. What does x, t, v, and s mean here? For those of you that have done chemistry before, the intensive variables here, talking about the mole fraction, the temperature, the pressure, the volume, the enthalpy, and the entropy. Remember delta H and delta S, change in enthalpy, change in entropy. Enthalpy is the state of calm. It's like a state of calmness or equilibrium. But entropy is the state of randomness. All right. So um, in intensive variables, we look at three areas: the strength. It describes three areas rather: the strength, the quality, and the shape. Okay, of the um of the stream that we're looking at. Okay. Then please, when I use the term stream, I'm talking about an inlet or a flow of fluid. You understand? So it's not your river that you have or the stream as you go. I say in this context for simulation and as far as ICS is concerned, when you hear the term stream, are referring to a fluid line or a fluid flow. Okay, all right, so it's good. It could also mean sometimes you might not see stream, you might see feed. So that's not the front end engineering design that I said earlier. This one is just the stream, a fluid that is flowing into a particular compartment in the design. Okay, so we have our extensive variables. Our extensive variables, we have the FQ and delta P. Delta P is the change in pressure. Q then looking at the heat changes and all that. So it describes uh, the um, size and quantity. Remember, intensive variables is for quality, strength, and shape. SQF. Then extensive variables are for size and quantity. Now, the next thing to talk about is defining a stream. When we are defining a stream in IC, you are going to see how it looks like very soon. When we are defining a stream in IC, you look at the chemical components, you look at the, the chemical component, that's each component composition of that stream. There are different compounds or elements that are making up a stream. This is what I mean, like in crude oil, for instance. Not just that you have, yes, you have it as crude oil going into maybe maybe a separator, for instance. Hmm? But that crude oil contains multiple components. All right, so it contains multiple components from methane to um, butane or to propane to hexane, and even in those hexane and butane, we might or maybe butane, heptane, that's five carbon atom and the rest of the hydrocarbon, five carbon chain hydrocarbon, you know, for that's pentane, for instance, or hexane. We could even have their isomers. Isomers, that's they have the same molecular formula but different structural formula. Okay, so you could even have that in those components. So all those describes the what chemical components. Then we have what the state. The state is referring to the vapor fraction, the pressure, and the temperature. The vapor fraction, the pressure, and the temperature. Those factors describe the state of that stream. So when you have crude oil flowing into the place now, we are trying to define the stream. We first look at okay, what are the components of that crude oil? In what fractions do they appear? Each one, those maintain themselves to the hypotheticals. Hypotheticals are those ones that have from seven carbon atoms above that we might not be able to just describe uh, extensively, but we know that they are also there. So they take um, they they have their various fractional composition. All right, and they have each of them have their mole fraction, the amount of each of them present in the crude oil. That's what it is. That's what we're talking about, relative to others. All right. Then the state is now talking about at what temperature is it flowing, under what pressure, how many isomers, or sorry, um, how many bars of pressure, or how many atmosphere of pressure, depending on the unit that we're using, standardized unit, and then the vapor fraction too. Then also another thing that is described in the stream in in defining a stream is the quantity. The quantity is talking about the flow rate. All right, the flow rate. Um, it could be in moles per VMQ or kilomoles per meter cube, as the case may be. You know, how many moles is present in that fluid that is flowing and at what rate is it flowing. So now, mole per VMQ is the volume that is present. Then at what rate the time that is using to flow. So that would be like volume over time. You understand? That defines what now? Our flow rate. The flow rate is usually volume over time. So it can be DMQ per second or meter Q per second and the rest of it. So that's so defining the quantity that is flowing at a point in time. All right, that's for the stream. Then we have to define the process unit also. Now, the process unit, we have all the units we experience pressure drop. That's some of the processes that take place in the system. You know, processing you have pressure drop that usually occurs as flow is increasing. Sometimes you have pressure drop, so we have to talk about that's what brings about this delta P. Yeah, delta P. Usually you see a triangle and P in front. So delta P. Then we have the heater and cooler, heating and cooling system. We have the pumps and compressors. All these ones now, what describes them, their process unit description is in terms of what? Duty, which is Q, all right? Which is also an extensive variable, as you can see up here. All right. Then we have the heat exchanger, the distillation column. Those ones have more specification. All right. So in HISIS, some factors that will now be worked out or looked at or calculated that help HISIS and help to be discovered from all these when we have all these values we have described. Some of them include density, viscosity, the CPCV or the fraction of it. That then we talk about the enthalpy changes, that's delta H and thermal conductivity or the molecular weight, the K value, that's the constant, and a lot of a couple of others too. Right, so degree of freedom specification user input um, and user specified. Now, anytime you see blue in ICC, it means that it is to be specified by user. Once you see red, it's calculated by ICC. Then once it is black, it cannot be changed. It's a figure that has already been computed. You understand that? Alright, so first thing first, what we need to do is we want to have the installation in the system. Right? If we have to run it here to not do it, we might not be able to run that definitive and do this class as it were. So please just follow the description and understand it very well. Once you have the ICC installed on your version, it is more difficult to open your versions and other versions. Yes, that's true. So it's best that you have a new version or outright the old version from the like with the new version when you are installing the software. Okay, you can get the software installed in your system. You can get them in the market. Very good. Ask for engineering software collections, and you can get and ask for advanced high speed. It's maybe from 7.3 upwards. You'll be able to install your Windows XP. I'm sorry, Windows 7 upwards. For 3.2, we install on Windows XP. Okay, that's just by the way. Anyway. All right, so this is what the whole stream looks like. I know it's looking a bit maybe but this is a beautiful illustration of what it looks like. Yeah. Right? Of what a simulation looks like. You can see here, we named it what now? Maybe 40 blend. We've named the stream. These thick blue arrows that you can see, the thick blue arrows, they are representing streams that have already been solved in HISIS. Now, all these ones like this here, for instance, this is like a compressor. Why this is an expander? Why this is like an expander? You can see it. combine or it combines two streams. You have two streams coming in here. Then you have a like a water inlet or cooling system. Alright? And then you have like you have something like a freezer con, condenser. Yeah, that's why it is in this kind of color, like green or blue. Okay. Now it condenses and it brings it into this um expander, right? This is like this is just a sample of a simulation. By the time you've done simulation, this is what it looks like. Alright. So you could have further compression of different streams. You can see how the streams are splitting. This stream here goes into this place, which is a stabilization process, and there it is further split into different components. The other stream comes into this too. And under this stream stabilization, you see that it is further split into some other components, just like that. Till you have we have some splitting and some combination of streams until we now get our final product at this point, where some of the streams that have been extracted at different points are now collected are then collected at this point at each point of this mixer. These ones you are seeing like this 4 or 5, they are called mixers. So they mix this component. We have a gas here, add gas. Then we have after that these dry gases are also mixed here. We have dry gas here. Then we have a combination of other things. Now, what this means is that all the propane, if for instance dry gas now, all the dry gases that have been collected from each of these points here, from each of these points, are all combined and brought into this point, this mixer. Okay, so we have it here. And from here we can, if you right click on the design simulation platform, you'll be able to tell more properties of each of these streams, their flow rate, their temperature, their pressure, those variables that we mentioned before. When you see it showing dark blue like this, what it means is that these streams have already been solved. You, I believe you're all following the explanation, and with more practice or study, you'll be able to still learn more. Because I'll tell you one trick about this simulation too. The more frequently you get to study them and use them, the more you will even be able to discover some 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 personal tricks or shortcuts or methods that you could also use when simulating that could help you. All right. So normally we try as much as possible to make them as neat as make our simulation process and design as neat as possible. This is a well structured and connected simulation platform already. But I'll show you an example of something that is random. You can see everything is arranged properly, and we have the collection clearly shown. Here now we have all the propane in this whole area coming, and they are all directed to this mixer. We have propane at this collection. We have butane at this collection. We have condensate at this collection. Okay, this is just trying to show you an example of what happens in crude oil um, in the fractional distillation process. All right, all these TTT, they are the trays inside the fractional distillation column. So we also have to stimulate them and bring them out like this. All right, now look at this. Compare this to this. So we say what a good design looks like. This is what it is. Now look at this other one. You can't even see anything. It's still the same thing the person tried designing, but the way he arranged the strings or the collection has made it very clumsy. Nothing is shown, nothing is stated. We don't know what any of these things stand for. Compare it to this one. You can see that the difference is very clear. Alright? So that's what that looks like. Okay. So I'll before I go on to okay, yes, we're going to do characterization. Do characterization. We're going on to that now. But before then, it's important I show you this um, assignment. So take a screenshot of it. This should be assignment 4. Assignment 4. Deadline for submission is on Monday 18th. Deadline for submission is on Monday 18th. The deadline for submission is on Monday 18th. 12 noon. Yes, 12 noon. So deadline 18th. 2020. 12 noon. Okay. So let's take a shot of that. Define independent variables. Define, explain the following independent variables with respect to I6, then defining a string and also defining process unit. Then you have why it's recommended to make use of englobing equation of state in modeling the system. What is the short form of englobing equation of state? Then um, what advantages does EOS have over the Kessler include package selection and explain the basic equipment in IC simulation. So, if that is already taken, we go on to our next topic, area which is fluid characterization and fluid characterization. Fluid characterization. All right. Under fluid characterization, what are the what are we trying to achieve in fluid characterization? What we want to achieve basically is we want to understand the importance of fluid characterization, be able to use the component library, and then to also be able to use the right equation of state. Okay. Now, um, let me see. Okay. Fluid characterization. Why do we need this? Why do we need to know the characterization of fluid in ISIS? The fact is that ISIS also has a very big library, and we define for us to know how the fluid works. We have to define and we have to be able to understand its that's what we mean by characterization. You know, the properties of that fluid and everything. That's how and what how it operates, it's composed, what it's composed of, and how it's dynamic is the dynamics of the fluid, the details about the fluid, everything that we need to know. Alright. Now, so how to characterize fluid? How do we characterize fluid? First before we familiarize ourselves with the substance on the first step. So if for instance it is say a mixture of chemicals that that is going to be the substance or substances that will need to be working with in the simulation. We first familiarize ourselves with it, what properties does it exhibit and all that stuff. So apart from that, we now look at it, what are the composition or the components of that particular fluid, or substance. Now, now, in this case, we are dealing with oil and gas. So our major focus in the simulation here is crude oil. So, and I've said something before, if you remember, that the crude oil, when we're talking about reservoir simulation, all right, we said something that the crude oil that we have in any a location will differ in the composition, as in the molecular composition from location to location. This is what we mean. So, where you are there, maybe Kaduna, or where you are there, maybe Venezuela, the crude oil, you have crude oil in Venezuela, you have crude oil in Angola, you have crude oil in Nigeria. Now, the crude oil in Nigeria, you might discover that the molecular, okay, the one you collected in Nigeria, and maybe you want to take it from, because gotten from the shores of the Atlantic around Bayelsa region, maybe Bonny area. Oh, no, not Bonny, maybe from southern region area and all that stuff. Or from you have another one from extra words, the Delta area region. You have crude oil from there. You have crude oil from maybe Iguna, Akwa Ibom, you know, if that's coming from their offshore location, you know, and then you discover something that all these crude oils, they all will contain methane, they will contain propane, they will contain butane, they will contain methane, they will contain fractions of the other compounds, which of all the components that are made up or that make up crude oil this way. But the property of each of these components will not be the same in every of these locations. Are you getting me? Now, what does this mean? It means that I cannot use the composition of crude oil from Yoko in a fiber to do a simulation for a composition that I'm getting from. Hello, I believe you can all hear me. Okay. So I cannot use the composition of crude oil that I'm getting from maybe Venezuela. I can't use it when I'm doing the simulation for crude oil from Angola. I can't use the combination of crude oil, the composition of crude oil of the stream of crude oil that I'm going to be simulating that I'm getting from Delta. I can't use it for what I'm getting from Akwa Ibom. All right. So for every specific sample or fluid that is being designed, we would have gotten the composition from the laboratory. The samples must have been taken to the laboratory and it should have been analyzed. So that analysis is what we will then use in also our simulation process. So it is special compound also. You have to know that each compound have their own special. That's what I just explained. Now, for instance, now some of those um, streams may have definitely we have different level of compositions of other compounds in it, like amine, like the acid or sour gas. When you say acid gas or sour gas, you're looking at the surface. gases that contain sulfur, you understand, in them. Alright, so now the level of sweetness, when I say sweetness, I'm talking about the amount of sulfur in the fluid. If the fluid has a lot of sulfur in it, it is described as a sweet fluid. And if the crude, that's crude oil, if the crude oil has little sulfur in it, it's described as so if it has little sulfur content in it, it is described as sweet crude. But if it has a large number of quantity of sulfur in it, it is described as sour crude. Sour crudes don't have very high market value because of the process of removing that sulfur. You know, sulfur in the crude will affect it will affect the system. It can cause damages to engines and other components too. Then and it's also highly poisonous. However, when it's extracted, those sulfur components are used for making fertilizer. So they still have the application in the oil and gas industry. Okay, and just for your record. Okay, so another thing we need to know the appropriate equation of state for the fluid. And then we now start our simulation. Alright? So the components and equation of state. When we're talking about components, we look at the paraffin, the non-hydrocarbons, the light gases, the aromatics, and the benzenes or the aromatic, yeah, which is also benzene, the naphthalene, ethyl benzene, and the rest chlorine, and the rest of the different components that could uh, be that could make up the crude oil. All right. Then among those paraffins now, we have the one carbon atom, the ethane, the methane, that's the ones that have two carbon. We have the ones that have three carbon chain. We have the ones that are normal six carbon chain. We also have the that's like NXA, for instance, that's the normal six carbon chain. But you also have I hexane, which is an isomer of that. Okay, an isomer of hexane. Once you have the carbon chain in the carbon arrangement changing, you have the carbon arrangement changing. For instance, methyl 2-methyl pentane is an isomer of hexane. 2-methyl pentane is an isomer of hexane, but they have the same molecular structure and formula, but different structural formula. That's what it is. That number of carbon atoms might be the same, number of hydrogen atoms might be the same, but the way they are bonded to each other is different. So you have a whole lot of combination of these inside the crude oil. Alright? So from the equation of state now let to define the correlation, the relationship between pressure, temperature, and volume. In this case, in this case, we have uh, pressure and volume. They have indirect proportionality. You know, um, that's PVT. But the temperature is directly proportional, or the product of the pressure and volume is directly proportional to the temperature. Where we have this as our constant like this, and the mole n is the mole ratio. Okay, these are constant Z and R. Alright, so we have PV equals Z and ROT. It's this equation that describes the equation of state. Or we have two forms of them, which is Robinson. We also have um, the Kessler, and we have this Schwabi Redick curve as in SROK. Schwabi Redley curve. Yeah, tongue twister. Alright, so this is what our um, component inputs in high looks like. Alright, is the first point that will come to. I want to click on the component button. Once we move to when we are starting. Okay, before then, so the component list, this is what you the component list here is to help us choose the basic component of based on the information that we have. I said something about getting the data from the lab. If something must have been taken to the lab, so in the lab, it will tell us
Engineer,
the yes.
man,
Can you hear me? Can you hear me?
please.
You said
Yes, time up.
my time is up. Whoa.
Yes, you've used
You took 5 minutes from my time, oh, please. So just give me 2 minutes. Let me round up quickly. All right. I don't know. Sorry, I'm in spirit already. Okay. So as I was saying quickly, the components here we'll be able to pick out those components from the ISIS. ISIS has a very large library. All right. So if you can take a screenshot of that, you'll still be getting this material soon. All right. So we have the fluid package where all the components of that fluid will be showing as we are selecting them. This is where we select. We can either select using the simulation name or using their full name or using their formula. So we search it out from this point here. If you type it, so you'll be looking at the records that you have been given from the lab. The information you will always be given when you want to do a simulation like this, you will always be given some basic information from the lab. One of the basic information is the composition of that fluid. So all you now need to do is to select the components by coming here to describe those components. Okay, we have methane. We'll select methane. We'll add pure. We have ethane. We'll type ethane here. If we are using simulation,